Hello, I'm Oliver Gao, Director of System Engineering Program here at Cornell University. I have been very fortunate to host this what I call system conversations with all the brilliant minds that we bring to Cornell for our Azure Roundtable System Seminar Series. So today, I'm very delighted to have Mr. Gary Smith, who is a senior expert system engineer at Airbus Defense and Space. He is an overall architect for engineering processes and provides technical leadership in the digital transformation, which we know nowadays is such an important area. He is an INCOSE certified expert system engineer professional and a senior editor of the System Engineering Body of Knowledge, which we know as CBOK, which is perfect for the system society, and it's a very important source for knowledge and insight. So ever since 2019, Gary has been the Vice President for System Practice in ISSS, which is International Society for System Sciences, and also their relationship manager with INCOSE. So this year, in 2024, he was elected as the incoming president of ISSS. So Gary, thank you for taking time to visit with us.
You're very welcome, and it's a real honor to be invited. Thank you very much.
We always wanted to invite you here. Gary, as I was reading your work and also when we were talking, I think people would be very interested in a look at your career and particularly how you ever since your college education and you started your career, how your whole path evolved. And especially it's a good reflection of your own development and also the system science community, because it seems to me that your whole career has been so closely interwoven with the system science and the system community. So I believe, like including me, many of our audiences would love to hear more about how your career and your path evolved. So please tell us more about you and your work.
Okay, so I guess it all started really when my parents bought me a chemistry set when I was about 14.
Wow.
Yeah, so what I found amazing about chemistry is you could have two substances, both colourless. You mix them together and you get precipitation, you get gases, you get colour changes. Mm-hmm. So I was always fascinated by this transformation that took place. Mm-hmm. And what I loved about chemistry was finding about how and why all of this happened. Mm-hmm. So when I left school, I was very lucky to get a placement in the chemistry laboratory as a junior technician. I did my education part-time, mm-hmm. So I started work at 16, and then after doing Technicians Education Council education, I then took 2 years essentially leave of absence to do my chemistry degree, and then when I went back to my company, I started working in relational database systems, and then software engineering, and then that led to systems engineering, various different roles, both in terms of architecture, design, coding, all of those sort of things.
And all these things you taught by yourself?
My original engagement into computing, I did teach myself. Yes, so I was working in the chemistry laboratory, and we had a computer which was purchased, but we had the computer and then no one knew how to use it. So I taught myself how to write Pascal. And then started writing software applications to help us in our work. And it ended up saving us several hours a day in terms of doing manual computations. After putting this in place, I had more time, so I was able to do more reading. I got more into sort of science fiction. The other thing I should mention is, I have a great love of the work of Carl Sagan and Cosmos and all of that. So I'm going to go and see Carl Sagan later today. His resting place. Mm-hmm. But I was with my company for a while in telecommunications, and then during the telecommunications crash, I decided to think about going back into chemistry, and I did some exploration of biosystems with the Open University. and using systems design techniques in the context of biosystems. I did some work looking at cancer and inflammation, and published a paper with the Open University, Cancer, Inflammation, and the 81 and 82 receptors. And then that started to expose me to the topic of systems thinking. And that's what then later led me into system science. But for the last 16 or so years I've been working for Airbus Defence and Space. I was originally brought into the company to develop technical management as a discipline. And I've had various different roles developing processes and capabilities in terms of technical management and systems engineering. But I've also been on large lead systems integration programs like border security, for instance. I'm not quite sure which is what has driven me through this particular path. But looking back, I think I've always been a systems thinker naturally. And there's always that question of, can you teach systems thinking, or is it something which is natural? I think that systems thinking comes in lots of different forms. Some people are more abstract and some people are more, focused. So I'm not quite sure how I ended up where I am, but my mother said to me when I was about 14 or 15, she said, you have a thirst for knowledge, and I guess that's what it's all about, really.
So Gary, you actually had what I would call a very diversified or non-traditional career path. You say that you started working when you were 16 years old, and then along the way you took time off to get your college education in chemistry, and then you went to pick up a position in chemistry. But in that position, you started coding and programming and doing some software engineering related work. But as you indicated, your motivation is really your pursuit of knowledge and your thirst for knowledge. And also, as you mentioned, that the system thinking that seemed to have come with you in your blood. So with that, you always been keeping your curious eyes open to observe the world and to absorb the new knowledge. And so I think that is quite impressive. So through all of this process, Gary is particularly, I think, nowadays with your position being the newly elected president of ISSS, that probably, you want to give it a lot more thought about our world and our society with respect to system science. So what could be the major system challenge that our society is facing, and how the ISSS as a society, as a community, can help advance our knowledge and our intelligence in dealing with this such complexity. So what are those key challenges, and how can the ISSS society help? Would you mind sharing some of your thoughts with us?
Yeah, so what you tend to notice in really complex problems is, first of all, the diversity of the interests and the stakeholders, and all of the different silos that are resident, in the various different disciplines. Silos are great because that's the area where you can develop a deep knowledge in a particular subject. But in those really complex problems, you need to be taking not just the entire perspective over all of those things, but you also have to be thinking about the past, the present, and the future. And what we tend to find in our politics and our decision making is that the decision making tends to be much more focused on the now and the short term. And that kind of thinking has been really useful to get us to where we are now. But in the Anthropocene, where we're changing the very geology of the planet to the point where we're now threatening potentially our own existence, we need to be thinking much more long term and acting towards those potential futures rather than just thinking about the next few years. And what we generally find in our politics, for instance, is that the politicians and the decision makers are mostly just thinking about what's going to happen next in terms of their re-election. Yeah. So potentially making promises which look good and make them look good, but from the perspective of the planet, those short-term decisions are not good for our future. And when we look at the COP, the climate change meetings, they've been talking about the same thing for the last 20 years or so, but we're still on the same path. We're still on that same path, and I think that's because of the decision making is more short term than long term, and promises don't get kept because the people change. Yeah, we also see this in our organisations. In our major corporations and across our industry, organisations tend to change fairly rapidly. Every 2 or 3 years. And somehow we need to be balancing those short-term goals with the long-term future. And I think, I know that taking the systems perspective is absolutely vital for that. And what I really want to the place I really want to get to is that we have a system science which is being practiced and researched and helping our decision making. We need to have a system science, which is akin to physics and chemistry, established as a global systematic enterprise. Nobody owns chemistry or physics, but as an enterprise, it exists across the whole of the planet, and we need to have that with system science because it helps to take that higher level thinking. Moving away from, let's say, traditional reductionist focus, which has been very helpful to get us where we are now, but to get us to the future, we need to be taking that much more holistic systems perspective. And I think system science will help us to do that. And it will also provide the scientific foundations for the systems approach and systems engineering, and indeed project management and all of our human activity systems.
So Gary, this past summer at the INCOSE Summer Symposium, where you were a panelist, you were talking about how chemistry got established as a discipline centuries ago, and also the pre-chemistry age. So you actually compare the current status of system science and engineering to the pre-chemistry age. So yet to be established as a discipline. So I think that is a very good angle. So how optimistic are you for system science and engineering to someday become established like chemistry? And I would like to be optimistic, but I can see the difficulty because chemistry deals with some fundamental elements and how they react with respect to energy and also their chemical components. So it's dealing with more specific things. But system science and system engineering are apparently dealing with things way beyond just fundamental physical or chemical elements, because system science and engineering, we are dealing with human in the loop, in the cyber, physical, and the social systems. So with that, do you see a future for system science and engineering to evolve into an established field like how chemistry had experienced?
I do, yes, Oliver. So where I think we are with system science at the moment, we're in a situation just prior to chemistry, maybe 150 years before chemistry, where we're in a situation of essentially alchemy at the moment. Yeah. So everything that we do in systems engineering, for instance, and project management, for instance, everything is really based on heuristics. It's based on what we've learned through practice over the last 20, 30 years, maybe a little bit longer maybe. There's what we have in terms of project management and systems engineering is actually pretty good. Yeah. I think in terms of systems engineering processes and project management processes, the processes are pretty good. The problem is that there's two problems. One is, first of all, they're not being applied in the way they should be. Mm-hmm. Yeah. Also, we have this almost like clash in the disciplines of project management and systems engineering, when actually they're both trying to achieve the same aims. So in terms of where we are with system science, we have a great diversity of systems theories and systems concepts, and also the methods. We have at least 20 different frameworks on systems thinking, for instance, which are, and if you're teaching systems thinking, which aspects of systems thinking do you teach? Do you teach this or do you teach that? Actually, when you look at all of these different things, it's actually possible to integrate them in a way which is systemic, based on foundational system theory. Yeah. It is possible to actually bring all of these things together. And that is a first step to creating system science, having a way of integrating our diverse set of knowledge in a way which is actually complementary and not necessarily competitive. So it's synergistic. And myself and a number of other people, we've been working on this for the last sort of 10 years, trying to find a way of integrating. And I really do think we're on the cusp of that first step of integrating stuff within an integrated framework. This framework may not be the ultimate periodic table, because as we know, the Mendeleev table also evolved over time. Yes. But I do think we've now got to the point where we have a candidate starting point which does actually work. Yeah, and that's one of the things I'll be talking about later today.
That's wonderful. I will definitely look forward to that. So, Gary, when we speak about system science, and especially when you talk about system science, its evolution, you make an analogy to chemistry, right? You're talking about the fundamental science and look at the scientific evolution. In the meantime, there is also the engineering and the practical aspects. Like there's also systems engineering, and but it's really because system engineering is so broad, it's really hard for people to really have a unified framework to recognize it. So, for example, MIT calls it engineering systems, while Cornell and many other institutions calls it system engineering. And no matter what, even we combine system science and system engineering, particularly from the traditional scientific and engineering community, many people are mostly talking about the very physical scientific part. But how about human factors, the social element? So in today's world, when we talk about societal challenges, either climate change, food security, all these things, there is no way we can go around human factors that are involved in the complexity of all these complex systems. So how can we use system science and system engineering to deal with system complexity that include diverse stakeholders? Not only the stakeholders being diverse, and even for the same stakeholder, and then in the past, at the present, and in the future. So, which means that these so many stakeholders, they can have short-term as well as long-term views in interacting in a dynamic sense. So, what do you see as the key pillars that can help us establish system science as a fundamental discipline, and also as a field? What are going to be the key areas you feel that we should tackle into to help system science and system engineering to be developed and to evolve along.
Wow, what a lot of information and questions in there, you know. So let me try and unpack that a little bit. So again, drawing the analogy with chemistry, and this I think will help to answer the question.
Yes.
So in chemistry, we have essentially two main dimensions of understanding.
Mm.
Yeah. So the first aspect is understanding about the elements, the chemical interactions. So it's the understanding of the subject itself.
Mm.
Yeah. And then there's the performance of chemistry, which is actually being able to not only understand nature's way of doing things in terms of chemical reactions, yeah, but applying chemistry in terms of using that understanding in terms of how to do chemistry. Mm-hmm. You know, how to transform chemical substances from one form into another. Mm-hmm. Yeah. Now, when we look at system science is concepts, theories, principles, and practices which are truly transversal across any discipline. So it doesn't matter whether it's chemistry or physics or biology or social systems. Systems are everything and everywhere in the universe. Everything is a system. And one way of thinking about this is systems are essentially organized entities. Mm-hmm. Yeah, and when you draw on that understanding of the nature of the physics, everything in the universe is essentially organized information. Mm-hmm. Yeah, and when we're transforming systems, we're essentially transforming information from one system into another system. Now, the other thing to appreciate. Well, let me just continue the story. So everything in the universe is a source and sink of signals. Everything, yeah, and that interaction may be through photonics or simply through gravity, but everything is in relationship with other things, yeah. So everything in the universe is a source and sink of signals. When those signals interact with something which is capable of receiving those signals, there's the potential for an informational event. Mm-hmm. Now, informational events over time add to the very being of those systems. When a system receives more information and integrates it into its existing structure, either mentally or physically, its complexity increases. Mm-hmm. Yeah, and those physical or mental structures have the ability to cause forces to come into action. Either for repulsion or attraction. Mm-hmm. Those forces then cause a physical change. They're able to direct energy and mass into the transformation of substances. Mm-hmm. Yeah. So you've got this conceptual side of information and knowledge, which then have an impact on forces and the energy and mass. And when you get an energy and mass change, new systems come into play. And those systems have the potential for new relationships, new affordances, new signalling. And this spiral in the system's experience is universal everywhere. The other key aspect of system science is this understanding of holarchy. Everything in the universe is a system, but everything in the universe is also a part of something greater. And that's really important to understand. Now, So the reason why I was talking about all of this is because, you know, when we talk about complexity is not necessarily a bad thing. If it wasn't for complexity, we wouldn't actually exist. And when you listen to, you know, the likes of Brian Cox and other social and physical scientists, they talk about the rich complexity of life on this planet and the rich complexity of the universe. And what we tend to find in engineering is that when we talk about complexity, we tend to talk about it as a bad thing. We want to remove complexity, but actually complexity is what we're all about. We're all about taking things and bringing new things into being. Mm-hmm. And coming back to the original question in terms of what is the potential of system science and what are the main pillars.
Yes.
Yeah. So when you come back to our engineering process, and actually this is what people do every single day in their lives anyway, we conceptualize, which is where we gather information. There's informational events. We then architect, And architecture is essentially, from my perspective, it's the appreciation of complexity. Not just understanding the features and the functions and the qualities of those things, but how you expect those things to change over time, and how to appreciate the interaction of the system of interest with its wider environment. Yeah. So that's architecting. Designing is mastering the complicated. It's working out how all of the various parts are going to come together to achieve the overall whole. And then after design, we implement, we realise. And when we realise the things, maybe sometimes there will be emergent effects that we hadn't anticipated, because the solution that we put in place, the system that we put in place, will have interactions, for instance, in our social systems or in our very environment that we hadn't anticipated. Yeah. And what we need to do is we need to get much better at that architectural appreciation at the front end and that conceptualization, so that we can better understand what the potential interactions might be. Yeah. And then we will be in a much better position to be able to create the world that we really want to be in, rather than, I would say, the more sort of bottom-up approach where we create new technologies without really understanding what the implications are going to be. Yeah.
Gary, I really like the framework that you have used to summarize, as a fundamental framework for system science. Particularly, you mentioned conceptualization, architecting, design, implementation, and then monitoring the interactions, repeating this cycle and keeping spiraling up for our knowledge and intelligence advancement. So I was not aware of this before, but as soon as you told me this, I love it and I embrace it immediately. So, and then this kind of made me think, taking me as an average person, when I heard this framework that you summarized, and I saw that it makes perfect sense, and I even think, okay, in my future research, I will start implementing and follow this framework. So what I was wondering is that you can see this conceptual framework, it's so straightforward and for me, and I can easily pick it up and assume that when you tell other people, this fundamental framework that support a system science or system approach, and I believe many people will, like me, they'll like it and they will embrace it. But then I was wondering why such a system scientific approach and framework, while it's so straightforward, but why it's not getting penetrated into the whole society, and what is holding us up from implementing such kind of system cycles, and what are the barriers ahead of us, and especially the barrier you see to promote this kind of systems science and a system engineering conceptual framework to practice and to widespread of usage.
Well, the barriers, again, you can draw the analogy again with another subject, which was software engineering. Software engineering went through this same kind of gradual establishment of the discipline, and the reason why software was so hard was because it was intangible. Yeah, it was very difficult. You cannot really touch software. It's a conceptual thing. Yeah. So an awful lot of work has been done on system science in terms of many people have contributed to it, and I think it's just. Remember that system science is a relatively young science. It's only. Some people may argue that Bogdanov back in the 1917s, 18s, he was perhaps one of the first people to start to come up with this. He came up with a science of technology, which is a science of organisations, and that was kind of rediscovered maybe 15 or so years ago. But then you've got the Bertalanffy and general systems theory, which was back in the 50s, I think. It's taken quite a while, but not an unreasonable while, to start to develop the concepts, the theories, and the overall frameworks. And for the last, I think it's interesting to reflect on that transformation that took place back in those early days. So in the early days of general systems theory and that organisation, which was contributed to by many Nobel scientists. After an original wave of enthusiasm, there was then a fragmentation of the science into systems dynamics and cybernetics, complexity science, many different areas. So the discipline fragmented, and there's been some diversification of the knowledge, which I think was probably actually natural and also essential for the next stage, which is bringing all of those things back together into an integrated topic. So and of course you've got all of the different personalities and the vested interests, and no disrespect to the conditions that academics are placed in, but the very way that academia works is it forces you to specialise. Yeah.
Yes. Yeah.
And as a consequence, it's very difficult to take that systems perspective in the academic circle. So maybe it has taken this integration of the academia with the practitioners. Yeah. So maybe the reason why we have made more progress, or we've been able to make some more progress over the last 10 years, is because we've been integrating academia with the actual practice. With systems engineers, for instance. I think the systems engineers have added, and I'm not just talking about myself, I'm talking about many people. I think we've added that necessary joining of the practice with the theory. And I think that has helped.
Yes, I agree. And Gary made a very, I think, very valid point. I think kind of putting the audience in the context of interpreting why system science or system engineering as a field is facing difficulty. And you use analogy of software engineering, because software, as you said, software engineering is intangible, and the software is not like hardware. It's not like a cup of water. It's tangible. So, but the good thing is that after the past few decades of all these advancement, now everybody knows what software engineering is, because software engineering has helped our society so much and benefited our society so much, so it had significant impact. So system engineering and system science, because it takes a holistic approach, look at the whole thing, and definitely it makes it even more intangible. As a result, it makes it harder for the society to absorb it. But now looking at software engineering, the key step it made it popular. It's really because software engineering was able to show the significant impact to the society. To think similarly, and I was wondering, how do you think that system engineering or system science, or what kind of significant impact, particularly tangible impact, that our general society can see that, right? So I think the majority of the society, especially either in the current mindset, or even the current momentum, the trend is still mainly, I feel, in specialization, right? While system engineering, we are emphasizing a kind of generalization and also a holistic approach. And this current focus on especially knowledge generation and education, we focus on specialization because specialization has helped our society with efficiency, right? In our society and our economy, most of the time we have been in pursuit of efficiency. And we're in this efficiency paradigm where we value and we promote specialization, which seems to be right against the systems approach. Right, so maybe I think someday, but when we emphasize specialization, when we emphasize efficiency, and many times we lose aside for example, climate change, sustainability. So maybe like when we get to a point where we're really facing urgency of climate change and sustainability, maybe people will rethink, okay, instead of purely in pursuit of efficiency, we should think about sustainability. We should think about overall well-being, such that system science will really have a soil to grow in. So, your point of thinking could be because very pervasive paradigm in pursuit efficiency that could be preventing, right, the growth and further development of system engineering. And also, you see that when we totally change this efficiency-oriented paradigm, do you think systems science and system engineering as a discipline will rise and get established?
Yeah. So for me, it's all about balance. Yeah. So we need efficiency and effectiveness. Yeah. But we also need to ensure that the target of our efficiency and effectiveness is the right target. Yeah. So system science is not just about taking the abstract. It's about completely integrating both the holistic and the reductionist aspects. It's both. It has to be both, and it has to be in balance. Yeah. So I'll give you an example. So when I was working on my ideas of cancer and inflammation and disease, I read something like, I skim-read something like 20,000 papers or so, trying to get an understanding of what was going on. What makes cancers cancerous? What makes these cells, which are normally part of us and under control, what makes them become pathogenic? What makes them start to grow uncontrolled? What makes them start to take over the environment? What makes them become malignant? So I went through a period of reading thousands and thousands of papers, looking for clues to see how the intricacies of things all work together at a level of detail. But I had to go through that process of looking at all of the parts in order to start to get an appreciation of what the whole might look like. Yeah, and putting myself almost in the position of a cancerous cell and trying to work out what was going on by taking its perspective.
Yeah.
But if it hadn't been for the effort of going through all of those details, I wouldn't have been able to come up with that big picture. So it's a combination of both which is required to solve problems. You have to have the details, but you then have to be able to rise above that and work out overall what is going on. Thinking about the environment, thinking about changes over time, looking at the overall dynamics, the multiple cause and effects. Because in complex systems, it's not simple. It's not just a single input and a single output. There's a whole host of interactions which take place over time between the parts, the overall system, and its overall environment.
Gary, you start with talking about maintaining a balance of pursuing knowledge, both in a holistic approach and also dive into the depths of understanding the very fundamental elements. So I agree with you. It's like a dichotomy, or at two ends of a spectrum. On one end, for example, we use chemistry, we use physics to really understand the depths and the details at the elemental level. And then, in other disciplines or even at the system level, right, we want to look at the joint behavior and at the macro level. So, but system science seems to be demanding all of this. System science and system engineering requires very good and a detailed understanding at the very elemental level, and also in the meantime, we want to be able to capture and characterize the whole. So now I see that, yes, actually system engineering and system science as a discipline is more even demanding than, for example, a traditional established disciplines. So because of this demanding and also because of complexity in addressing this demanding requirement, so that's probably why, right, it takes much more effort, and it will be more difficult to establish such a discipline and such a field. But apparently, even we know that system science and system engineering, and they are still probably in the infant age, and they need to be developed further, which of course require generations and generations of people to devote to this field and develop this field. So which means that we also need to think about future generations. Now, it's a good time for us to switch to education. So can you share with us your view about systems education and how we can promote systems literacy?
Okay. So I'm of the opinion, I think it's shared by many people in the systems world, that we need to take another look at our education systems. Our education at the moment, it's a lot about teaching people facts, and you know that teaching people how to think has declined. Yeah. We need to incorporate systems thinking more into our basics educational material, you know, at a young age. Mm-hmm. You know, and I know that there are organisations like the Waters Foundation that are doing this, for instance. But the thing is about systems science and systems education is, again, you have to tailor it to the particular audience. And what Ray Eisen would call their system sensibility, you know, their preparedness to take on, systems knowledge. Mm-hmm. Yeah. So you have to pitch systems education to the really young people in a way which is conducive to their mental models. Yeah. Mm-hmm. And what's interesting is when we look at our various different heritages and the stories that our parents and our grandparents used to teach us, like Aesop's tales, for instance, mm-hmm. there are systems, concepts, and systems thinking embedded in those stories. Yeah, and we can be taking advantage of that. Yeah, so that's one aspect. You know, pitching the education for the very young in the way which is conducive for them. Mm-hmm. But then as you progress in your, let's say, scientific appreciation of systems, what we need to be able to do is we need to be able to communicate in a way which is conducive for those people, the essence of the, let's call it, the periodic table of systems for the scientists. Yeah, and that's what I'm hoping to be working with the educators, the professional educators on, finding a way of communicating those core system concepts and methods and overall frameworks in a way which is conducive for people to be able to take them on and then engage more, learn more, and be able to apply it better. Mm-hmm. Because the topic itself, as we mentioned, is abstract. Yeah. Mm-hmm. So you can't pick up a piece of iron, or you can't pick up a piece of copper and say, okay, these are the elements that I'm playing with. The elements that we're playing with when we do system science, they're concepts. We're playing with concepts when we transform and manipulate systems. Mm-hmm. Yeah.
So with that, I think, Gary, I agree with you. You have laid out very nicely, I think, 3 layers or 3 stages for promoting systems literacy. First of all, at a younger age, you talk about, developing sensitivity and literacy of system engineering and system science, especially, at the young age, which will be conducive to the mental models so that they can pick up as they grow and develop. And then also you mentioned about, as they grow probably in the college and university stage, right? Like we have such kind of system engineering or system science curriculum so that can continue to draw students to the field and expose them to more systematic and fundamental frameworks and methodologies for systems science and engineering. And then beyond, right, after their graduation, after they enter into the workforce, we should continue to engage them and expose them to the rich soil of system science and system engineering. For example, ISSS and INCOSE are addressing this kind of third layer of engagement and applications. So with that, I feel kind of establishing or planting the system thinking seed in early age seems to be very important. Like your own case, like you have always been interested in system thinking. So I want to talk about K through 12 education. Do you see some kind of practice or effort happening where people are picking up some of the importance and implementing system science from younger age and also keep engaging them?
Yeah, so the Waters Foundation are doing some really great work with what they call the habits cards. Mm-hmm. They have 14 habits cards, and on the front part of the card there's obviously the title, like Seeing the Big Picture, for instance. There's a really lovely picture on each of the cards, which is giving a visualization of the concept, and then on the reverse of the cards you have questions that the teacher and the child can play with when they're exploring that particular concept. So the Waters Foundation stuff is really great, and that would be the kind of thing which I think would be really useful. One of the things I'd like to bring into this, Oliver, while we still have time, yes, is in order for system science to be truly a global enterprise, what we need to do is we need to engage across all of the different systems, organisations and communities, and organisations who value a systems approach. And we need to build essentially a systems community alliance across all of these organisations. And all of those organisations need to be working together to practice system science and systems application, and to integrate our knowledge, and to work towards that common core of systems education, which is absolutely vital, because then that will give us a shared orientation. But if all of the systems communities can come together, then we will be able to not only engage in practice, the development of the knowledge, but we will also be able to start to influence more effectively the key stakeholders who make the decisions about how the planet runs.
Wonderful, Gary. It seems like you are talking about a grassroots approach, basically from the bottom all the way to the top, and then gradually, to where the decision makers will see the value of systems thinking, system science, and then implement it in their policies and in their practice. So I agree with you, kind of, if through all this grassroots movement and also education and effort, such that the top level as well as at different levels of society, we realize the impact, the value of system science, and I feel that will probably be a critical moment where this system science engineering can be established and accepted as a field, like how chemistry was established centuries ago.
Yeah, Yeah, and I think the time is absolutely right. You know, when you look at the publications, when you look at what people are saying on their websites and in the communication, you know, the value of systems thinking is really becoming very much appreciated. Yeah, and so we have an opportunity here to draw on that and to not just do systems thinking in terms of set of heuristics, you know, what we've learned bottom up, but also turn those heuristics into actually systemic principles. Yeah, so
Yes.
founded on the science.
Gary, you know, we've also been talking about Cornell System Engineering, which has a mission to train, educate, and our future systems scientists and engineers to keep carrying this flag forward. So, with your understanding of our program, what would you like to say to us, to our faculty, and to our students?
Be part of the bigger picture. Yeah. In terms of your students, I would really encourage your students to embrace complexity and certainly to embrace paradoxes. You know, a paradox is where your existing mental model doesn't tie up with what you're experiencing in terms of reality. Yeah, it's a what on earth is going on here moment. Yeah, and if you embrace the paradox, you will ultimately, in order to resolve the paradox, you will change your mental model. Yeah, and you will really learn something significant. Yeah, so embrace paradox, embrace complexity. Complexity is not a bad thing. Go off and do something different to what you are normally doing, and you will grow as a person. Yeah.
Wonderful. Gary, I totally agree with you. You know, out of box and being open-minded. You also use the word embracing, and I agree with you because it's not just okay. It's just not about keeping your mind open. It's really taking a proactive way and with passion. That passionately embrace a systems approach and a systems thinking, and because passion is the best thing that can carry us a long way, especially when we are facing difficulties. So I really appreciate that. I appreciate that advice. Thank you again, Gary.
Thank you very much.
This is
I
wonderful.
really appreciate the opportunity.